Today we're going to look at section 5.1, which is all about angles and radian measure. So the objectives today are we're going to recognize and use vocabulary of angles. We're going to talk degrees and radians, and then we'll be able to convert back and forth between the two. So let's talk about angles. Okay, angles are something that you've been dealing with back in geometry. Remember, angles are formed by two rays that share a common endpoint. Now we're going to have a little bit more vocabulary with it. We have one ray, which we call an initial side, and another ray, which we call the terminal side. So in the diagram up here in the top corner, you can see an angle ABC. B is the vertex because that's where the two rays intersect. I have a blue ray, which is the initial side, and a purple ray, which is the terminal side. Notice how that there is an arrow inside by the vertex, and it's going in a specific direction. That arrow is indicating the direction in which the angle is rotating. Okay, we're going to talk about it in a second, but the way that the angle rotates is going to be important. Notice that not only inside of the vertex do we have an arrow showing the direction in which the terminal side is moving, but we also have a Greek letter inside. So mostly we'll be using lowercase Greek letters such as alpha, beta, and gamma. But then in the symbol right there is theta. That's the one we probably use the most. But though these four are kind of the Greek letters used most often when we're doing these types of problems. Okay. Also, notice how the arrow is starting with the movement. It's starting on the initial side, and then it's going towards the terminal side. That's important. It will always start the movement on the initial side. All right, so let's talk standard position. An angle is in standard position when we have two things happening. The first thing is that the vertex is at the origin of the rectangular coordinate system, and the initial side is going to always lie on the positive x-axis. So here we're going to talk about two different types of angles, positive and negative, but the diagrams that I have them drawn in what we called standard position. So in the top right, the picture that I have, this is actually representing a positive angle. So notice that with the picture, we've got the initial side is on the positive x-axis. Notice the vertex is located in the middle at the origin, and the terminal side is, it could be really anywhere. Notice that the arrow showing the movement starts on the initial side and it's pointing and heading towards the terminal side. This diagram is moving in a counterclockwise rotation. So if you look over here on the left, it's describing it then as a positive angle. So positive angles are generated by going in a counterclockwise rotation. So this angle, which we call alpha, is representing a positive angle. If I look at the diagram down here below, once again, this is in standard position because the initial side is on the positive x-axis. Once again, the terminal side could really be anywhere, but notice that the direction of the arrow is going in a clockwise position because the arrow movement is showing that it starts at the initial side and the arrow is pointing towards the terminal side in a clockwise position. So negative angles are generated in that in that clockwise position. So this picture here, we've got that theta. This is representing a negative angle. So when we're talking about positions of angles, the terminal side is going to be where we're locating where the angle is at. So just a quick reminder, we've got 4 quadrants, and the quadrant 1 always starts in the top right, and then it moves in a counterclockwise position. So quadrant 2 is the top left, bottom left is quadrant 3, bottom right is quadrant 4. Even though the terminal side a lot of the times is going to fall within one of those 4 quadrants, it doesn't necessarily have to. So down here, it says the terminal side doesn't necessarily have to, have to lie in a quadrant. It could fall on the X or the Y axis. So when that is the case, we have a special name. We call this a quadrantal angle. So once again, notice that my picture, I've got the initial side. It's that lighter blue arrow on the positive x-axis. Notice that the direction of this angle, which we call beta in this picture, is going in a counterclockwise position. That means that the angle is a positive angle. Notice that my terminal side, which is that darker blue, is on, in this case, the y-axis. So that's why it's a quadrantal angle. So measuring angles using degrees. You should be familiar with degrees. We've been measuring angles with them since the very beginning when I'm talking about angles. So just a quick reminder, angles are measured by determining the amount of rotation from the initial side to the terminal side. So that definition might be a little bit new to you, but just the amounts of these angles are not going to be new. So we measure in degrees. Remember, an acute angle goes anywhere between 0 and 90 degrees. But noticing the picture, once again, that light blue line is the initial side. Notice that the rotation of the arrow is heading towards the darker side, which is the terminal side. And so because that measure then is going to be between 0 and 90 degrees, it's acute. A right angle is going to then be 90 degrees. If you're thinking about the 4 quadrants, it makes up a fourth of the rotation because it's a fourth of the quadrant. An obtuse angle is going to be any measure between 90 and 180 degrees. And then a straight angle, which is half of rotation because it goes from the positive x-axis to the negative x-axis, that's 180 degrees. All right, so degrees you should be familiar with. Now let's talk about radians. So when we measure angles using radians, we have to understand how we get these radian values. So it says 1 radian is the measure of the central angle of a circle that intercepts an arc equal in length to the radius of the circle. So some of this is vocabulary from geometry when you're talking about circles. But notice that a radius goes from the center of the circle to a point on the circle. So here what I highlighted is a radius. But notice that there are multiple radii in this picture. And remember, all radii of a circle are congruent. So notice that this is called a central angle. So those 2 radii make an angle. And it's a central angle because the vertex of that angle is at the center of the circle. Notice that what I have then here on the outside that's helping form the circle, well, that's an arc. And so notice that they labeled that R as well because that's the same distance as the radius inside my circle. So that's what determines us to have 1 radian value. All right, so consider an arc length of S on a circle with a radius of R. To find the measure of the central angle, which in this picture, notice how they named it theta, we would have to do a little bit of algebra. So to find the measure of theta in radians, we would take the arc length of S and we would divide it by the radius R. So we're going to use this formula and let's take a look at a few examples. So once again, my formula, I'll write it up here at the top, is that in order to find that theta value, the central angle, I want the arc length and I want to divide it by the radius. Okay, so we're finding the radian measure because this is in radians of the central angle. We're given the radius in the first example is 5 feet. So once again, radius means that that's the R value. Arc length is 30 feet and that's representing the S value. So they're giving us everything that we need in order to find theta. Notice that both of my units are feet, and that's important. They have to be the same unit in order for us to calculate. So we can solve for theta right away. I want arc length on the top, so 30. I want radius on the bottom, so 5. And when I divide, 30 divided by 5 is going to give me 6, and this is in radians. So we have 6 radians here. In the next example, we have a radius of 1 meter. So once again, that's the R. And we have an arc length of 600 centimeters. That's the S. Notice this time, the units are not the same. One is in meters and one is in centimeters. Like I mentioned in the last problem, you have to have the same units in order to use that formula. So now we got to think about unit conversions. Remember, 1 meter is the same thing as 100 centimeters. So it doesn't really matter which unit you decide to use. I could change that 1 meter for the radius into 100 centimeters, or I could turn 600 centimeters if I divide by 100, and I know that it's 6 meters. So once again, those are all equivalent. You just have to pick one of them and stick with it. Okay, so if I stick with centimeters to find my theta, I know that I want arc length, which is 600 centimeters, to be over the radius, which is 100 centimeters. When I divide, this will give me 6. Just like if I had used 6 and 1, we're still talking about this theta in terms of radians. Now, I do want to point out that both my answers are 6, but that doesn't necessarily mean that every single time you're going to get the number 6. So just be aware of that. But it is super important that you are understanding that the units have to be the same in order to complete these problems. All right, so now let's get into the relationship between degrees and radians. We're talking about, once again, a rotation around the different coordinates, or sorry, quadrants, I mean. So we are thinking about like one full circle. So if you remember from geometry, one circle, the full rotation is 360 degrees. A circle with a radius of r, we can find the circumference of a circle by taking 2 pi r. Now, why am I talking about circumference? Well, if we think back to the formula that we just did some practice problems with, which is right here. Remember, if I'm talking theta to be arc length divided by the radius, well, arc length of an entire circle is the distance around the circle, and distance around a circle is circumference. So that's why I'm using that 2 pi r. Okay, so arc length or circumference goes on the top, so 2 pi r. If I want it over the radius, that is r. So then notice that those divide nicely. The r's cancel, and you're left with 2 pi. So what is the point of having 2 pi? Well, let me explain. 360 degrees is equivalent to 2 pi radians. That is a measurement and a unit conversion that you're gonna want to remember. You're gonna be using this from here on out for the rest of your math career. So 360 degrees is 2 pi radians. If we divide both sides by 2, 180 degrees is the same thing as pi radians. Okay, we're gonna use this last new measurement here. 180 degrees equals pi radians. We're gonna use this information to now do some converting. So to convert between degrees and radians, we're using that relationship that pi radians equals 180 degrees. If I start with degrees and I want to turn it into radians, we're trying to multiply to get rid of degrees. So notice that we're going to create this fraction where I need the radians on the top because that's what I'm trying to find, and I need degrees on the bottom because when you multiply it by degrees, the degrees will cancel. Same idea if I then start with radians and I want to turn it into degrees. I just have to flip the fraction around. If I want to end up with degrees, I want degrees on the top. So I have 180 degrees on the top. Because the radian values in the denominator, I'm multiplying by radians. So that fraction, if it gets multiplied by radians, well, then the radians are going to cancel. So let's use that information and let's do some converting. So let's start with these 3 examples. I'm giving you all degrees. We're going to turn them into radians. So if I have 60 degrees, once again, I'm going to multiply that by a fraction. It's 180 degrees equals pi radians. Because I want to solve for radians, that means that I want the radians on the top. So I want the pi radians on the top, which means I want the 180 degrees on the bottom. Think about this. You can put the 60 degrees as over 1. When you multiply fractions, you multiply straight across. So this is what I was talking about. If there's something on the top that's on the bottom, they're going to cancel out nicely. And in this case, the degree for the 60 is going to cancel out the degree for the 180. So the degrees go away and you're left with radians, which is what I wanted to convert to. When I multiply straight across, we'll have the 60 pi on the top. We'll have 1 times 180, so 180 on the bottom, and this is in radians. So you don't have to write the word radians on the top. It can just go off to the side. The only last thing that I need you to do is I need you to reduce. So if I have 60 degrees, or not degrees, but just 60 on the top and 180 on the bottom, I'm going to be able to simplify. Okay, not only are they both divisible by 10, which will get rid of the zeros, but then 6 and 18 are both divisible by 6. So that means that we'd be left with just the pi on the top. 18 divided by 6 would give me 3. So 60 degrees is the same thing as pi over 3 radians. Okay, let's look at the same idea, but now I'd have 270 degrees. So once again, I start with 270. That gets multiplied by a fraction, where if I want radians to solve for, I want the radians on the top, which means that the 180 that is equivalent to it, that degree goes on the bottom. When I think about this then as over 1, so I can multiply fractions straight across, degrees on the top, degrees on the bottom, those cancel. So multiplying straight across, 270 is now with the pi on the top. 1 times 180 is 180 on the bottom, and this is still in then radians. So notice that the two numbers are definitely divisible by 10, but then 27 and 18 are both divisible then by 9 as well. So when I divide them both by 9, we'll have a 3 pi on the top, a 2 on the bottom, and once again, this is our final answer in radians. So 3 pi over 2. The last example here with converting degrees to radians, notice that my angle is negative. So if it starts as a negative degree, when you convert, it's gonna be a negative radian. So just be aware of that. So we start with negative 300 degrees. I wanna multiply that by a fraction because I want to have radians. The pi radians go on the top. So then the 180 degrees are on the bottom. When I think of it as over 1, the degrees are gonna cancel. When I multiply straight across, we'll have negative 300 pi in the numerator and 180 in the denominator. This is still in now radians. Notice that these are both divisible by 10 because I can get rid of a 0. And then negative 30 and 18 are actually still both divisible by 6. So that's going to reduce down to negative 5 pi on the top and 3 on the bottom. Notice how I didn't lose the negative sign. So we have a negative 5 pi over 3 radians. Now let's go in the opposite direction. This time I'm starting with radians and I want to turn it into degrees. So this time if I start with pi over 4, there's already my fraction. I'm going to just put the radians in the numerator. And remember, now I want to multiply and I want to get rid of the word radian. So that means that I want the pi radians in the denominator, and I want to solve to get it to be a degree, so the 180 degrees go in the numerator. Notice that not only then do the radians cancel, but also, in this case, the pi's cancel as well. When I multiply straight across, the only thing that I'm left with on the top is 180 degrees. The only thing I'm left with on the bottom is 4, and I can divide. 180 degrees divided by 4 is going to give me 45 degrees. And don't forget your symbol for degrees. In the next one, notice how we're starting with a negative radian, which means my final answer should be a negative degree. So we're going to have negative 4 pi over 3. Remember the radians, I can think about that in the numerator. And so because I want to get rid of radians, I need the pi radians in the denominator, which means that the 180 degrees go in the numerator. Then notice that the radians are going to cancel. And once again, there's a pi in the numerator and there's a pi in the denominator, and those are going to cancel as well. So when I start multiplying straight across, negative 4 times 180 is going to be negative 720, and there's degrees with that. The only thing that I have in the denominator is 3. When I divide, it looks like we get negative 240 degrees. And then finally, in this last one, 6 radians. So once again, 6 radians, if it's not a fraction like it is not here, you can put it over 1, just like we did with all those degrees. But because I want to get rid of radians, I need the pi radians in the denominator, which means I want the 180 degrees in the numerator. So the radians are going to cancel, but notice this time there is no pi on the top, which means we have to keep the pi on the bottom. When I multiply straight across, 6 times 180 degrees is going to be 1,080 degrees. When I multiply the denominator straight across, 1 times pi is pi. So let's do this. Let's then actually divide. Don't use 3.14. There is a pi button in your calculator. So hit the pi button when you divide, and then let's round it 2 decimal places. So 1,080 divided by pi is going to give us 343. Notice that it's 0.774. So that means the 4 will keep the 7 the same. And once again, don't forget the degree symbol. All right, please pause the video and try this checkpoint problem. Okay, hopefully you noticed that in my first example, the units are the same, which is good. So arc length goes on the top, radius goes on the bottom. This time the radius was bigger. So instead of making it a decimal, because 3 divided by 7 is going to be not a very pretty number, I don't want to do any rounding. I want to leave it exact. So I just reduce down that fraction, and notice how, once again, my final answer is in radians. And then with number 2, when I was doing converting, I wanted to convert the first one from radians to degrees. So notice that's why I had to have the 180 on the top and the pi or the pi radians on the bottom, so then the radians would cancel. You end up with 108 degrees. In the second example, I start with degrees, so that means if I want it to be radians, I have to have the 180 in the denominator. When I multiply straight across and I simplify, we get 7 pi over 4. So that's us recognizing using vocab with angles, talking about degrees and radians, and then converting between the two.